Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! One question which dogs human thought is, where does wealth come from? How can I feel like my resources are abundant and that I have power and influential status in my community and that these will continue into the future? I have to tell you that I don't know the answer to this question, and I would question why you might think that I would. But some people think it can only come from dominating others and ensuring that they'll work to your benefit today and in the future. Others say that it can only come from establishing a community of people and family around you who can hold you up in hard times. Others think that it can only come from government, formalizing cooperation we owe to others and which is owed to us in turn. And others think that wealth is a zero-sum game. The only way to get it is to build a metaphorical wall and then take it away from other people. Other people notice that wealthy people seem to have a lot of gold. So instead of focusing on where wealth comes from, they ask the question, where does gold come from? And this is a question we can answer. Ancient philosophers wondered a lot about it. Ancient alchemists worked a lot at it. And all of them figured that there must be some reason why the Earth has lots of gold, but that gold is underneath the surface of the Earth. Some people thought gold was solidified sunlight, the way ice is solidified water vapor. Others thought you could only get it through transmutation. That's the alchemist word for what we'd call a chemical reaction. But transmutation involving a rare and unachievable object called the Philosopher's Stone, or if you're in America, the Sorcerer's Stone. But after all this trying, no one managed to make it work, because it takes more than chemistry to transmute lead into gold. It takes the death of stars. In modern terms, the word is nucleosynthesis, the combination of atomic nuclei. And gold and all the precious metals we see on the Earth were transmuted into being during some of the most violent processes in the modern universe. And so it was, to my delight, that the LIGO interferometer and an international collaboration of astronomers announced in October that they had witnessed an example of this process earlier this year. The process which sprinkled the galaxy in gold and precious metals, the collision of two neutron stars. Today on the Titanium Physicist podcast, we're talking about smashing two neutron stars together. Speaking of pure gold, I've been a fan of this guest for many years. He's a stand-up comedian and a familiar voice on Canadian television and radio. He frequently performs on CBC's radio's The Debaters, and he even has a podcast, The Well-Reads, which is a monthly left-wing book report show. The first book in his curated humor imprint, Robin's Egg Books, has just been released, and it's called What I Think Happened, an under-researched history of the Western world by Evany Rosen. And also, good news, he just released a comedy album. It's called Fatherland and can be purchased off of iTunes. Welcome to the show, Charlie Demers.
Thank you so much for having me.
Oh, Charlie, I have a real treat for you today. My two oldest and favorite physicist team, for the auspicious start of our 7th year in podcasting, I present to you the A-Team. Arise, Dr. David Tsang! Dr. Dave did his undergraduate degree with me at UBC and his PhD from Cornell University, and is currently at the University of Southampton, UK, where he studies theoretical astrophysics. And now, to much acclaim, arise, Dr. Jocelyn Read!
Roar!
Dr. Jocelyn did her undergraduate degree with me at UBC and her PhD from University of Wisconsin-Milwaukee, and she's currently at California State University, Fullerton, where she studies neutron star mergers. All right, everybody, let's talk about smashing stuff together. All right, Charlie, did you hear the news about these neutron stars smashing together?
Is this a setup? I feel like a punchline is coming.
Two neutron stars walk into a galaxy.
Yeah. So, no, I have not heard this one.
Have you heard about gravitational waves at all?
I mean, I've definitely heard about gravity, and I've definitely heard about waves. I'm not so positive about the combo. So, theoretically, if I had forgotten what they were.
Hypothetically, if we were going to explain from scratch.
Yeah.
As if you might not have known what they were.
Yeah, pretend I'm a guy who doesn't know about science.
So, there was this guy with hair and a mustache.
Stalin?
Yes!
Bigger hair.
Oh, Einstein. I know this because
There you go, yeah.
there's my dad had an Einstein poster, because my dad was a teacher in the 80s and 90s, and you were required by law to have a lighthearted Einstein poster in your classroom. And in this poster, my dad looked exactly like Einstein.
Is it the one with his tongue out?
Is it the one where he rides a bike?
Or is he saying imagination is more something knowledge?
Or is he sticking his tongue out?
Imagination sounds right. I feel like that's the one. Right next to a poster of Garfield telling you to read.
That's right. Let's start talking about gravitational waves.
The big thing about how Einstein changed the way we think about gravity by saying it's not, two things pulling each other with forces, but it's this influence on the background fabric of space and time warping and stretching around stuff, and that causes things to fall.
Is that what he said?
That's what he said.
Exactly those words.
Yeah.
So when you say it's like a background thing that is warping around things, I mean, I know that was pretty specific, but is there any... what kinds of things wrapping around what kinds of things?
So, the distance between things stretches, and if something tries to go in a straight line, the warped space-time curves it around into, say, the orbit of the moon around the Earth.
Do you know those old mattress commercials?
With the bowling ball?
Yeah, with the bowling ball. Think about the bad
and
mattress.
Stalin, right? It was,
And Stalin, yeah.
Yeah, okay, yeah.
Yeah, and good old Uncle Joe is dropping a bowling ball while you're trying to sleep.
This commercial is very Vancouver specific. I don't know if everybody else is going to get our Stalin bowling ball mattress commercial reference.
I don't think Stalin ever came to Vancouver.
Yeah, that's what they named the Georgia Viaduct after.
Stalin is pretty widely known. He's not only famous in Vancouver, guys.
He's only famous for, but in Vancouver specifically, he's only famous for mattresses, right? So, and the Georgia Viaduct.
Sure.
You're talking about the commercial where there's bowling pins set up and then the bowling ball drops on the other side?
So, now we're talking about a bad mattress here, where if you put the bowling ball down, the mattress sinks around it, right?
Mm.
So Einstein said the universe is like a bad mattress.
Right. And so physics is the quest to find the P underneath it.
Yes.
Right.
Okay.
Physics is like the black light you're shining on that mattress.
Oh, Jesus Christ.
Oh, Jesus. I stay in too many hotels not to be disturbed by that.
So, for instance, the mass of the Earth, you can imagine space and time as this mattress, and the mass of the Earth sort of pushes down into that mattress. And if I took a little marble and I tried to roll it around on that mattress, instead of just rolling in a straight line, it would curve around because of the indent that mattress is made. And just like if I took a little asteroid and threw it at the Earth, it would sort of come around, maybe enter into an orbit.
So before Einstein, people thought of the universe more as like a pool table.
Yeah, and then it's sort of like invisible strings or invisible springs that sort of held things together.
Things.
Nice.
Like these sort of invisible distant forces was the picture that Newton had.
And Einstein said that was not the case. Like, how did he know that?
One of the things that Newton gravity has is that if something changes where it is, across the universe, the pull of gravity changes instantaneously. And now Einstein's like, no, if something moves, that change kind of has to ripple out through the mattress.
Right. One of the things that led Einstein to develop his theories of special and general relativity was the observation that the speed of light was constant. It didn't sort of matter how you were moving. You would always measure the speed of light to be the same. And so one of the consequences of this is that information can't actually travel faster than the speed of light. So if I took some mass and I shook it around, that information can only travel at the speed of light. So it sort of ripples outwards at the speed of light. And so space-time also carries out this information at the speed of light.
It's like your bad mattress analogy. You're on your bad mattress with your fat, ugly husband, and your fat, ugly husband rolls around in his sleep. Even on the bad mattress, you've got fractions of a second before you're thrown to the floor by the shifting mattress because it takes time for the wave, the information that your fat, ugly husband has rolled around to travel to the nice side of the bed.
So how come the speed of light being constant means that's true?
That more led to this idea that there's this thing called space-time, that space and time can stretch and squeeze and aren't just like a background thing. So to make the speed of light be constant, no matter how you're moving, space and time need to kind of shift around.
I feel like your question kind of asks kind of the history of experimental and astrophysics up until the development of Einstein. And so what would happen is we thought Newton was right up until the end of the 1800s. But slowly there were a bunch of observations and there were a bunch of experiments that suggested it was wrong. So one of these experiments said, hey, it doesn't matter which way we're going around the sun. The Earth goes in a circle around the sun, right?
Yeah. That I was 100% aware of.
If light was traveling through a medium, like if we were in water and we're talking about waves moving through the water, depending on the direction the Earth was traveling around the sun, the sound waves through the water would be different. And similarly, we'd expect the light waves to travel at different speeds depending on how we were moving around the sun. And the answer is, no, it doesn't depend where we are on the sun. Light is always traveling at the same speed. And everybody was like, what? That doesn't make any sense. And then, in addition to that, there were some astrophysical observations talking about what Mercury was doing in its orbit. And it wasn't quite orbiting the way Isaac Newton would have predicted it. And so the table was set for a new physical framework to describe gravity in. We knew that Newton's theory wasn't quite right because it didn't predict the right stuff. And also, we had all these other new pieces of information, like light always travels at the same speed, regardless of how fast you're traveling relative to it. That's weird. And so Einstein put all these different pieces together into his theory of gravitation, which involves the curvature of space-time. Does that make a little bit more sense?
Mm-hmm.
One of the big implications of all this space-time wibbly-wobbly stuff was that if stuff's moving around really fast, it can stir up gravitational waves. Although Einstein was like, but they're way too tiny that it's totally irrelevant.
So one of the big implications of the theory of general relativity is that space-time is dynamic. It responds to matter, and it warps and changes. And the result of sort of wiggling around that matter can be these sort of waves that propagate outwards from where the matter's moving. And those are gravitational waves.
So the idea is that the universe is more like a smoothie than a salad. It's all like mixing and moving around. It's more like a slurry than like a kind of, crystallized constellation of things.
Yeah.
It's more like Jell-O than a chocolate bar.
Oh.
Right. I mean, mine was healthy, but...
Well,
Smoothie is good too, but I think the salad confused me.
Right.
The smoothie's just too viscous.
Right.
Okay. If you tried to shake it around, it would just sort of plump, and then, the Jell-O will keep shaking.
And there's always room for it.
Yeah.
So let's reiterate what Dave just said, because it's philosophically bonkers. A person should rightly kind of lose their mind when they hear it. We're used to thinking of distance as being kind of an immutable quantity, right? So like the distance between me and the door is 3 meters right now. And we're used to the idea that 3 meters is just kind of set in stone. It's because of where the door is and where I am relative to the door. And the only way for that distance to change is if I get closer to the door or somehow the door gets closer to me. Mm-hmm. Einstein takes that idea and goes, well, not quite. Because in Einstein's theory of general relativity, in his theory of gravity, gravity is caused by space and time warping. Distance scales in this case are dynamic. So, what Einstein says is, well, the distance between me and that door might be 3 meters now, but you never know, some weird gravity thing might come in and make that distance 2 meters. You stay in place, the doorway stays in place. It's that the distance between you and the door is now a dynamic quantity. And the thing that makes it change is essentially the presence of mass and what mass is doing, because mass causes space-time to warp. But it's weird. And so what these gravitational waves are is they're waves carrying information about how objects have moved around, shifted positions. But the form that these waves take is it's a wave of changing distance scales. In other words, if one of these gravitational waves were to pass between me and this door that's 3 meters away, suddenly the door might be, because of this wave, the door might go from 3 meters to 1 meter away, and then back to 3 meters, and then up to 5 meters. You never know. I mean, that's pretty bonkers.
That's basically like black holes are merging, like...
Yeah, I think we'd be dead.
I mean, you would be stretching and squeezing along with the door in this scenario.
Yeah.
It's the principle of the thing. That the distance scales are dynamic, and these gravitational waves carry information about gravity, but because they're essentially dynamic distance scales, they pass through you, and suddenly the distances around you kind of change.
It sounds like the distance scale is still... Because you're saying that the door would now be 2 meters away, but like a meter is still the same amount, right? Or would it?
Yeah, if you had a ruler and you tried to use that wooden ruler to measure the distance, the ruler would also shrink, and so you wouldn't be able to tell.
Although it would resist it.
Yeah, that's true. Because it's solid, would try to push against it.
The way we measure this is we use lasers. And as each laser travels, it's a light wave packet thing, but it's got a little clock going tick, 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 and it's traveling at the speed of light. And so when it travels, it bounces, it comes back, and you can kind of calibrate by what state it's in, how long it's traveled. And then the gravitational wave comes in and it stretches the distance, and now we send another little packet of light through, and it has to travel a little extra, so its clock's gone a little bit further by the time you compare it again.
By using these light pulses, you can measure distance in a way that sort of is not in reference to something that has the physical separation.
I mean, that is part of the challenge, is like, how do you measure the distance changing when that stretching and squeezing affects everything?
Is there any marker outside of this fluid process by which you can measure?
I mean, there was a lot of debate about this, and like one of the early thought experiments was if you had 2 beads on a really stiff rod, the gravitational wave would kind of slide them back and forth, and then that would mean that they could rub and make heat, and that would pull energy out. So it was like a real physical thing happening here. It could do stuff. The beads on a stick, which was from like a famous conference in 1957, where this guy called Pirani came up with this, and then everyone tells the Richard Feynman story and gives him all the credit.
So Jocelyn mentioned the most efficient way to measure these changes in distances is to use light. Unlike a meter stick that might get squished or stretched as a gravitational wave passed through it and throw off your ability to measure it, light, if you take 2 mirrors and you bounce a pulse of light between them, the amount of time it takes for the light to go down the mirror and come back will depend on essentially the pure distance between them. And so if a gravitational wave passes through, it'll either take more or less time than usual.
So the light is affected still by all the bending and pushing. It's not outside of it.
It's traveling through a background that's being stretched and skewed.
The light is getting stretched too, but we're always like sending in new photons, and each photon goes in and bounces and comes back with its report, and then we send in a new little bit of light, and it goes out and measures the distance and comes back with its report. So they're all getting stretched and squeezed by the gravity too, but we can still figure out what's going on.
So we use light to essentially measure distances in this case. But the problem here is light goes really, 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 really fast.
The speed of light, if I'm not mistaken.
Like, it's not like we can say, okay, laser, we're going to shine you down this hallway, and we're going to measure when you leave, and we're going to measure when you come back, because that time interval is teeny tiny. Even if we like made a 100 kilometers long tube, it would still take, an unmeasurable amount of time to get back. So we do something really clever. We take two essentially mirror corridors, long tubes with a mirror on one end, and we put them perpendicular to each other, 90-degree angles. So we set one going north and make it, 4 kilometers long. And then we set one going east and we make it 4 kilometers long. And then instead of measuring how much time each photon takes to go down the tube and bounce back, what we're doing is we're sending photons down, both of them at the same time. And if a gravitational wave comes through, it's going to change the two perpendicular arms in different ways. It'll stretch one and shrink the other, or shrink one and stretch the other. Because they're perpendicular to each other, they're 90 degrees, they'll feel different effects from the gravitational wave that passes through them. And then we compare the two photons when they come back home. We can combine them in a process called interference. We can figure out if they've taken the same amount of time to go back and forth down these hallways, or different amounts of time. And if it's different amounts of time, we can be like, sweet, we can measure that by comparing the two photons using interference. And then we can say, yes, a gravitational wave is passing through here.
So it's like triangulation.
Yeah, kind of.
But like, where are these tubes? Like, where is the light going out?
Well, they're in Washington and Louisiana. So the light is generated at the central base station from a laser system. And then it hits a mirror that's half transparent. So part of it gets reflected and part of it keeps going. And they go off at 90 degrees from each other, bounce against these big chunks of mirror really far away, come back, and then they get recombined at the central station. And so light travels as a wave, so it's, cresting and trough and crest and trough. And they come back together and they see whether the crests and troughs line up or not.
Wow.
To blow your mind a little bit, the precision of this is so much that we detect the relative change of distance from one arm to the other arm is the same fraction as a human hair compares to the distance to the nearest star.
Jesus. That that's really wild. And so these gravitational waves are not they're not just constant background. They happen.
Well, we think there might be a constant background, but it's really, really low level. Stuff that's kind of brighter in gravitational waves or stirs up the distances more are these sort of infrequent transient things. So the thing that's caused the strongest gravitational waves that we've measured is black holes crashing together.
Black holes crashing together?
They start out orbiting each other, and then the gravitational waves make them fall together. So they orbit closer and faster, which stirs up more gravitational waves. So they fall together, and that keeps on happening until they crash together. Except they're black holes, so they don't have surfaces, so they don't really crash together. They just kind of get really close to each other, and then whoop, there's a bigger black hole that's all wonky, and then it sort of settles down.
Whoa.
So basically, any big chunks of matter that are sort of moving relative to each other will emit gravitational waves. If they're sort of, imagine like a dumbbell that's rotating. That's sort of the simplest thing you can have that will emit gravitational waves.
So you can wave your hands around and emit gravitational waves right now.
Should I do that for the show? For the sake of the episode, should I make some gravitational waves with my hands?
We can all do it. And now we're creating a background of gravitational waves fluctuating through the universe.
So different things are putting out, there are myriad sources of gravitational waves at any given time.
That's right.
Yeah.
So the bigger the masses and faster they move, the more they emit gravitational waves.
So with Donald Trump's hands, there would be smaller gravitational waves.
That's right.
Exactly. Like,
Very beautiful gravitational waves, though.
Yeah.
The best gravitational waves.
Yeah. Right.
Huge gravitational waves.
The name of the game here is acceleration. The more a massive object accelerates, the more energy is going to go into gravitational waves. And so you end up with a process Jocelyn was just talking about called binary inspiral. It's when you've got two objects that are orbiting each other. Both of those masses, to go in a circle, they have to be accelerating. So the closer they are to each other in orbit, the faster their orbit's going to be and the larger the acceleration you'll need in order to stay in orbit, right? So, the moon is far away from the Earth and it has an orbital period of a month, whereas the International Space Station is much closer and it's got an orbital period in the hours. So, long story short, the narrower the orbit is, the faster the objects are going to go, and the more acceleration you need. And the more acceleration you have, the more gravitational waves you're going to produce. And so, in Einstein's theory of gravity, you can't have two objects in orbit around each other forever. In Newton's theory of gravitation, you can get orbits that last forever. So you could say, the moon will orbit the Earth forever. In Einstein's theory of gravity, though, orbits lose energy to gravitational waves. The effect is really, really small usually, but it's measurable. This was the first evidence that anybody had of gravitational waves was you could look at systems that were orbiting each other and check to see if that orbit was changing. And it was changing due to essentially the system losing energy to gravitational waves. So if you have two objects that are in orbit and they're losing energy to gravitational waves, their orbits will get closer together. Their orbits will decay. And the closer they are together, the more acceleration they need, they radiate more and more intense gravitational waves. And so in a black hole binary scenario, what you can get is once they get fairly close to each other, they're radiating a ton of energy in terms of gravitational waves, and their orbits are decaying faster and faster and faster. And this generates a ton of gravitational waves and a really, really recognizable signal. Because as they get closer together, the period of their orbit decreases, the frequency is going to go up and up and up and up, and they'll go faster and faster, faster, and the amplitude of that signal is going to increase because they're orbiting closer, and so they're going to lose more and more energy. And you get a ramping up telltale signal called a chirp.
A chirp?
Yeah, chirp.
This is like what hockey players do to each other. Like it's a kind of a chippy, confrontational kind of signal?
It depends on the mass of the objects.
Oh, okay. Okay.
Right. So the black holes, they come into the audio band. These waves are coming in, and it turns out they're the same frequencies as human hearing can hear as sound. So we can just map the waves into sound. And if it's black holes, it's just this foop kind of thing. Because by the time you can hear them, they orbit around each other a few times, and then they thump together. And so it's just foop, foop. It's just a few cycles of sound. Well, there are things 10 times to 30 times the mass of the sun are swinging around each other at a third of the speed of light.
So this merger of these two black holes gave off few by 10 to the 49 watts. Imagine a light bulb instead of 100 watts, with two zeros behind. Well, one with two zeros, it's one with 50 zeros behind it. And that's sort of the amount of energy it gave off. So during that brief second, when it gave off these gravitational waves, it was releasing more energy than every single star in the entire universe.
Right before they collide into each other, that's when they're going around the fastest and stirring up the space-time the most. And they lose huge amounts of energy that goes out into the universe. And so if you could measure the energy of gravitational waves the same way you measure light energy, it would outshine all the stars in the universe.
Wow.
Just for a fraction of a second. And then it's one black hole and it just settles down to darkness and then nothing.
So do you recall Einstein's famous formula about E is equal to mc squared?
No, I'm not familiar with it. No, I've never heard that.
From the poster!
No, yes, I have. I was kidding. I don't know. I mean, in fairness, I've heard it 7 million times in my life.
But what does it really mean?
And I have no idea what it means.
Right. So what it means is that to figure out how much energy you would get by converting pure mass to pure energy, you just multiply by the speed of light squared.
Okay.
And In this case, three entire suns of mass disappeared and got shut out as energy.
Yes, that's right.
And what happened to all
It
that?
just turned into gravitational waves.
It ripples off.
And then does it just keep bouncing around, or does it eventually kind of peter out?
It just spreads out through the universe, so it's going off mostly in all directions, kind of a peanutty shape actually, but it's radiating out from the system, and so the system collides and you get this sort of bright ripples going out in most directions, and as they travel they kind of get weaker and weaker, right? So like you imagine plonking a rock into a pond, and as it ripples out, the ripples get smaller and smaller as it moves out away from the central plonk. So by the time it's reached us, like 1 billion years later, it's just this faint wiggle in our space-time fabric that's much weaker than it would have been, near the dramatic explosion itself.
So the gravitational waves that we see, is it like the light from stars? Like we're not experiencing it in real time. It's something that happened potentially eons ago, and we're just measuring it now? Or is this something that, like, if we have one of these big gravitational waves, that means that something's happening right now in the universe?
It's exactly like light.
Okay.
It travels at the speed of light to get to us.
So measuring a gravitational wave is the same as seeing the light from a distant star. Like it could potentially be measuring something that happened millions and millions of years ago.
Yes, that's right.
So then, like, what's the earliest or the soonest we could see something? Like, so is this something where, like, if something like this happened much closer to us, we would find out much sooner?
If, for example, something happened in a galaxy 140 million light years away, it would only take 140 million years to reach us.
Right.
I guess the thing to note here is, you asked a couple minutes ago if we were always being bathed in gravitational waves, and the answer is yes and no. We are, but most of the ones we're being bathed with aren't detectable. It's these really, really strong gravitational waves that are generated by binary merger that are strong enough for our instruments to detect. But we can only detect them if they're within range of the sensitivity of our instrument.
We've only really just turned on this microphone to the universe. Like and it's sort of just like the crudest mic. We can only pick up the very, very loudest things. And so we're still deaf to, or we still can't hear, basically, most of the noise that's out there.
Yeah, gravitational waves that are detectable come from events that don't happen very often.
Well, if you go through the entire observable universe, we think they happen every 7 minutes.
Yeah, so that's the notable thing, is that they're common enough if we listen to a wide enough stretch of space. Like, if we can listen over a region of space that's billions and billions of light years wide, then these things will happen frequently enough that we'll be able to detect them with our instruments. And so it's kind of like a size game, right? Based on your instrument's sensitivity, you're going to hear them more and more frequently, because even though it's a fairly rare event, it's sure to happen somewhere. It's like somebody winning the lottery, right? So nobody in your neighborhood is going to win the lottery. But if you extend your population size to the size of Canada or the size of North America, then hey, every week someone wins the lottery. Right. Even though that event is fairly improbable.
But you're saying every 7 minutes, 2 black holes collapse into each other somewhere in the universe?
Yeah.
Wow.
Only some of them are close enough so they're loud enough for us to hear.
I don't know what to do with this information.
That's a lot of where we are with this kind of science. I mean, it's new enough. It's kind of, well, people are like, well, how does this affect my day-to-day life? I'm like, this merging black holes across the universe. I mean, so cool.
But one thing to realize is that these detections only happened 2 years ago.
Yep.
And the very first ones?
The very first ones. And that's the first time we've ever measured anything with gravitational waves.
What was the lag time between Einstein proposing gravitational waves and the first time we were able to measure them?
The lag time was almost 100 years.
Oh, wow.
Yeah, it was like on the 100-year anniversary.
Yeah.
But then that's kind of poetic because, in the same way as you see the light from a star that's maybe been extinguished afterwards. He says gravitational waves, then dies, and then we get to see it, almost like an echo after he's dead.
Yeah, the news hasn't reached the scientific community that Einstein's dead.
Yeah.
But it's basically like we've built a radio that can listen to the universe all of a sudden. We've built this receiver that can suddenly listen, right now kind of only to the loudest things, but we've suddenly sort of been able to turn on our hearing.
Yeah, we've developed an entirely new sense.
Cool. See, that's really neat. You guys this is like an accelerating strength of metaphor going on here. Where I am, I'm more and more able to see there's such a tremendous gulf between specialists and turnip truck rubes like myself that we don't even know enough to be excited by some of these things. But that sounds very cool. The idea of being able to listen to the universe or having another sense and suddenly being able to tell. And it feels like early enough to be excited about it from the ground floor.
Yeah. Well, it's the beginning of being able to listen to the universe as well as see the universe.
Yeah. And we just had like another cool development in August. So you can be even more on the cutting edge if you ask us about that.
So the black holes that we talked about, that we detected a few years ago, those made a really loud noise that we heard in gravitational waves, but we didn't really see anything from it. Our telescopes didn't catch anything. But that's because black holes themselves, unless they have some matter around them, they don't make any light.
So two black holes can stir up space-time and fall together and emit, 3 masses of the sun's worth of energy and be just this completely dark event from the perspective of all our, previous telescopes.
Right. So if you have some matter around that can interact and emit light, then you have a chance of seeing some event on your telescopes.
So we're like the Tyrannosaurus Rex in Jurassic Park, where we needed them to move to see them.
Exactly. So you could think of sort of old long exposure astronomy, like just taking pictures of the static sky. That's like, a photograph, right? And then more recently, in the last, few decades, we've been developing the ability to look at transients, things that sort of go flash in the night. And we've sort of been able to get better and better pictures over time. So we're now starting to be able to see movies, animated GIFs of what the night sky sort of looks like. So we're discovering all sorts of neat things that sort of pop off, like different kinds of supernovae and different kinds of transients and sort of all different parts of the electromagnetic spectrum.
Animated GIFs are like the silent movies of today. That's really deep.
Yeah. But if you could see something that comes from the merger of two really heavy dense objects that are emitting gravitational waves, then all of a sudden it's like we're in the talkies.
So we started out with just the black holes with no light associated with them. So we're sitting in the car in Jurassic Park and we just see this thump ripple.
Cool.
Thump ripple. But now we're going to start combining the new transient, moving picture astronomy and the soundtrack at the same time.
That's really neat.
Yeah. So, in fact, in August, there was a simultaneous detection of a merger of two neutron stars that was caught in the electromagnetic spectrum with light and with gravitational waves.
So for the very first time, we heard and saw something like that happening at the same time.
That's right.
Yeah, we got this unprecedented multi-channel view of an astronomical event with 70 observatories around the world all joining forces to try and observe it with whatever astronomical techniques were possible, including 5 space-based satellites, all getting independent views in all kinds of light and gravitational waves of this one dramatic event.
It was the most observed event ever, I think, in terms of astronomy.
It replaced the Justin Timberlake, Janet Jackson halftime show. How did they know that event was coming? Like, how did everyone prepare? Like, it started happening and then people realized it was happening,
Yeah, so there's like this astronomical alert network, and for the last gravitational waves set of observations, this was done by people who had signed up ahead of time and agreed to like not talk about things because we weren't really sure if we were going to do it right on our first tries.
Mm-hmm.
So we had this basically like, Twitter platform for gravitational wave stuff. And every once in a while, I think there were 5 things that we talked about. We're like, oh, something interesting, gravitational wave with these properties from this patch of sky.
And so all that added up to there was going to be this big thing happening.
Well, so a bunch of these had gone out and telescopes would follow up to see if they could see anything. And there hadn't been anything particularly exciting until this one event came in. And the really amazing thing was that the gravitational wave signal came in. And then at basically the same time, a gamma ray observing satellite said, I saw a flash of gamma rays.
So gamma rays. So there's this interesting history.
Famous for creating the Incredible Hulk.
Right.
Yeah. So that's what I know them from.
Right. So there's actually a really interesting history of what are called gamma ray bursts, which are literally bursts of gamma rays from out in the universe. In that we had no idea they existed until the U.S. put up a satellite to monitor nuclear testing. They were trying to basically look for hidden gamma rays from hidden nuclear testing. And then they turned it on, and then
there's like a bunch of these things a day.
Yeah, a bunch of these things like bursting out in the universe somewhere, and the Russians weren't all the way out there, so we accidentally discovered the fact that there are these big bursts of gamma rays that are...
Oh, that's just what the Russians wanted you to think.
And for ages, like, we had no idea where in the universe these were even coming from. Like, are they in our own galaxy? Are they from across the universe?
So it's thought that they come from sort of 2 main things. The longer lived ones probably come from the collapse of massive stars. So big massive stars that sort of collapse in on themselves and then shoot out jets sort of up and down. And if we happen to be sort of staring down the barrel of that jet, then we see these gamma rays, this big burst of gamma rays. And then it's thought that when you have 2 neutron stars that merge and smack together, that they'll also do something similar, but that's a little bit more short-lived. It's a burst of gamma rays that only lasts a couple seconds.
How would you describe what a neutron star is?
So a neutron star is basically as close as you can get to collapsing to a black hole. Well, matter makes its last stand against like just being crushed to a singularity. So it's the densest kind of matter that we know of in the entire universe. And it's something that's like 1.5 times the mass of our sun, that started out as a big massive star that ran out of energy and went supernova and collapsed down until it got to this strange form of matter that halted the collapse at the density of a nucleus and about the size of a city.
Wow.
It is the most extreme matter in the universe.
And it stays like that?
Yeah, it's supported by quantum pressure. So pressures of particles not wanting to be in the same quantum states keeps it from collapsing any further for as long as you can imagine.
So these neutron stars you can think of them as like sort of giant nucleuses. They're so much matter crammed in that everything is as tight as the nucleus is in an atom. Do you remember the sort of science class picture of what an atom looks like? There's, the protons and the neutrons at the center, and then the electrons sort of floating around?
Vaguely.
The idea is like all the mass in an atom is in this tiny little nucleus at the middle. What is it, like a basketball in a football stadium or something like that?
Do they mix up the ball in the stadium from different sports on purpose?
It could just be that I am bad at distinguishing my sports.
No, it's okay. I just thought like having a basketball in a football stadium was just like one extra level of confusion for me.
Oh, here we go. Oh, I was totally off. The atom is a pea in a football stadium.
Oh, wow. Okay.
The way it goes is regular matter, the stuff around us, solid matter, it comes from electrons in different adjacent atoms interacting.
So, like, you are prevented from falling towards the center of the Earth because the thin layer of electron clouds on your feet is bumping up against the thin layer of electron clouds on the ground, and they're repelling each other.
Really?
Yeah, so at regular energy scales, different atoms interact by their electron clouds pushing up against each other. And so the size scale, it's like saying, hey, you can't build these two adjacent stadiums next to each other. You know, your one stadium bumps into another stadium. I guess you put your stadiums on wheels so you can smash them together.
Mm-hmm.
That gives you a sense of the size scales. It's not like the nucleuses or the P's in the middle of the stadiums are touching each other. Inside a neutron star, what happens is it's all P's all the time. Everything is made of P's.
Yeah.
It's a tinier size scale than we're used to here on Earth because of the crushing gravity allows these nuclei to interact. And so essentially, like Dave said, everything is the density of a nucleus. It's tiny.
Neutron stars are really weird and extreme. So they're massive enough and compact enough that they can stir up gravitational waves. But there's this weird stuff there, which, as it turns out, turns into mostly neutrons, hence the neutron star name. So this really neutron-rich, wacky matter of all nucleus-like particles at super high densities. And so the two of these things crashing together, it ripples out with the gravitational waves, and then they crash together and then sends out this jet of gamma rays really soon afterwards. And both of those were just detected.
Okay.
We also see something called kilonova or macronova. And what this is all the neutrons, imagine two neutron-filled piñatas, and you're sort of swirling them around and then smacking them together. And, some of the piñatas stick and form some object, maybe a black hole, but a lot of the candy sprays out. A lot of the neutron-rich candy sprays out. And that neutron-rich material, it's basically a whole bunch of heavy atoms and a whole bunch of neutrons. And what happens is what's called the rapid nuclear process, which all the neutrons sort of can smack into those atoms and get absorbed. And that generates really heavy elements. In fact, that's one of the few ways of generating really heavy elements in the universe. So we think that this is actually where most of the really heavy elements come from. Elements like gold, elements like platinum.
So these two neutron stars crashing together threw off what turned into like between 1 and 10 Earth masses of gold, along with a bunch of other heavy elements.
A lot of heavy radioactive elements. So the atoms in the neutron star were squeezed so much, all the neutrons popped out of them. And then when they're flung off, they're suddenly decompressed. They're no longer sort of squished down by the gravity of the neutron stars. And it gets flung out, and they all sort of run back into the atoms and swell these atoms up to be really, really heavy and make really, really heavy elements and really heavy radioactive elements. And this radioactive cloud decays into things like gold and platinum. And that decay, that radioactive heating and the energy given off of that is what we see as a kilonova or a macronova in the infrared. And there's also some evidence of it being in the optical as well.
So we actually observed all this, but we were only able to find this because the gravitational wave allowed us to triangulate where in the sky this was, and also told us it was like kind of close by. So we were able to like point telescopes at the right galaxies to find this new scenario happening.
How recent was it?
We observed it on August 17th.
But when do we think it actually happened?
So because we're able to pin down the galaxy that it happened in, we know pretty precisely that it was, and can I remember? It was 140 million years ago.
Dinosaur times.
Wow.
in a
different galaxy.
far, far away.
Not that far.
But would any of the gold that we have potentially have come from that event?
Not this one. A similar one, like in our own galaxy. So the gold probably stays in whichever galaxy it's produced in, but this suggests that some...
Oh, so like in the local economy.
Yeah, that's right.
Yeah.
Like supporting local small business. Yeah.
Yeah, most of the gold on Earth probably came from some event like this, and then it gets distributed out into the galaxy, and those eventually swirl around and form into stars and planets, and then we get the gold that's mixed into our planet.
So after World War II...
So it would have to be something in our galaxy that happened before the sun formed.
Do you want to get a better idea of how this formation of gold happens? How you go from smashing neutron stars to gold? Because I've got some pretty stupid analogies. Okay, so before we go, we need to understand the problem of where gold comes from. The idea is, you know how earlier in the show we were like, E is equal to mc squared? The deal is that that's essentially the mechanism that stars use to burn and to stay puffed up. Is they take, say, 2 hydrogen atoms and they combine them, and the resting mass of 1 helium atom is less than 2 hydrogen atoms alone. And so if you combine 2 hydrogen atoms, there's an excess of mass energy that then becomes heat. And so in combining 2 atoms into a heavier atom, you get energy back out. And that works. You can do that up until the atom iron. Anything heavier than iron, you can't combine in this way to get new atoms. And so one question here is, okay, all of the elements on Earth, carbon, oxygen, things lighter than iron, they came from essentially heavy stars or combining 2 elements into a heavier one up until iron. But then past iron, it's like, where did all that stuff come from? And the answer is really, really violent processes like a supernova sometimes generate them. But a huge candidate for where they come from is neutron star mergers. And the issue here is what neutrons do when they're left unattended. If you have a proton and it's just sitting on its own, or an electron just sitting on its own, they're stable. A proton's not going to do anything. It'll just sit there forever. An electron will just sit there forever. But if you take a neutron, as nucleuses in atoms have protons and neutrons, if you take a neutron and just leave it outside of a nucleus on its own, it will decay. It'll turn into something else. It'll turn into a proton and an electron. And so you don't see any neutrons wandering the wilderness alone. So the neat thing here is, how do you get a neutron? You essentially take an electron and you squeeze it into a proton. And that's fun. In the cores of in these neutron stars, it's covered in neutrons. Almost everything's made out of neutrons because the gravity is so strong that it's crushing all of the electrons into the protons, making just a ton and ton of neutrons. So when these things collide, they kind of pop like grapes being squeezed as they're about to collide, and they spew neutrons everywhere. I want you to imagine, like, okay, you're out at sea. There's nothing but 2 rafts full of survivors of a big shipwreck. Okay. So they're living on crappy flotsam that they've tied together, and there's just 2 masses of them. The flotsam, that's like protons. Your neutrons need to hold on to some of them to stay neutrons. Your neutrons are the people. These flotsam ships are just covered in people. People everywhere. And imagine that these 2 rafts made of flotsam covered in people. They hate each other, so they're going to ram each other. If they ram each other, what do you get?
This seems unproductive for a ship.
Yes, but that's human nature, right? So you get these big collisions. You get detritus, flotsam flying everywhere, and people flying everywhere into the ocean. So most of the people in the ocean just drown and turn into fishes and flotsam. But if there's people near a little bit of, maybe there's like a little bit of a barrel floating there, or another, piece of garbage, something floatable, a proton, the neutrons around it will kind of glom onto it and grab it. And if they can grab it, they'll be stable. And so you end up with these patches that whatever, any free protons flying around will just kind of suck up the neutrons around it, like the people gathering at whatever bits of flotsam they can. And so you'll end up with 1 bit of flotsam, which is like a barrel, covered in lots and lots and lots of people, which is like neutrons. So you'll end up with these clumps of essentially atomic nuclei that have way, 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 way too many neutrons in them. But it's kind of stable. And so from those, you'll get a little bit of radioactive decay. Maybe they'll throw a couple people into the ocean until you get a stable a stable mass, but in the end, or maybe, I guess in this metaphor, some of the people will die, some of the neutrons will turn into protons again, and then they'll be used to make a new raft. And so you'll end up with essentially new, smaller rafts that have way more people on it than you'd expect, which are gold atoms, polonium, palladium. Yeah, some of the people get turned into garbage and get used to add to the raft of stability that all the other neutrons are clinging to. Yeah, so that's where all the gold in the world comes from.
Wow. So at the end of World War II, when, the international sort of financial system moves to the Bretton Woods system where currencies are pegged to the US dollar and the US dollar is pegged to gold, you had, at the end of a conflict that was ended with the first use of nuclear power or nuclear explosions in the atomic bomb, you then had the whole world go to an economy based on these heavy elements created by colliding neutron stars billions of years ago.
Can you think of anything more precious? Yeah.
That's crazy.
What that tells you is that it's not actually a philosopher's stone, it's two of them. And they're neutron stars.
Right. That was the big problem with alchemy.
That's right.
They thought it would
Harry
just
Potter
one stone.
should have been crushed by the philosopher's stone's gravity.
The tides. Harry Potter and the impossible tides. Harry Potter and the
Tidally ripped
spaghettification.
apart.
Yeah.
That's incredible. Also, it feels like a hilarious analogy that in our wedding ceremonies, when you're bringing two people together, we exchange these gold rings that are basically the product of two hyperdense bodies colliding violently.
In fact, they're the only things to escape the fate of those two bodies that came together.
That's amazing.
Well, that was amazing. Thank you, Dave. Thank you, Jocelyn. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. David, you get a golden delicious apple. And Jocelyn, for your services, here is a mango. All right, I'd like to thank my guest, Charlie Demers, hero of the radio and the podcast screen, and go buy his album, Fatherland, which can be purchased on iTunes as we speak. Thank you, Charlie. Hey, everybody. Let's just do the announcements. First, please give us an iTunes review or tell other people about us elsewhere online. Why? Because people keep their love of physics as a deep secret, and they want to know that there's a show like ours online, but they don't know that we exist. Your friends and family will be happy to hear about us, and then you'll have someone to talk to about physics. Secondly, thanks to your donations we've received over the last few years, I was able to hire a professional to redesign our website. It looks great, and it should work on your phones and tablets just as well as on your computers. Why don't you mosey on over to titaniumphysics.com and have a look. I need to rewrite some of the things on it to fit the new style, so I'd be happy to get your feedback about what you think could use a little bit of work. On another note that's related, we're still humbly soliciting your donations. Your donations going to pay for our server fees and our project to transcribe the episodes as they come out, and thanks to your support, we've transcribed the entire back catalog of the Titanium Physicist podcast. You can send one-time donations through PayPal off our website, or you can go to our sweet Patreon site and give a recurring $2 donation. This particular episode of the Titanium Physicist podcast has been sponsored by a collection of generous people. First, I'd like to thank the generosity of Stian Henriksen and Steve Horgrave for their donations. I'd also like to thank Adrian Schoenig, Sandra Stradler, Louise Pantelina, a guy named Ben, Mr. Matthew Lambert, a fellow named Ayush Singh, David Myrtle, Mr. Ryan Foster, Janico Friefenberg, Steve Smethurst, Magnus Christensen, Bart Gladys, and Mr. Stuart Pollock, our Emperor Courtney Brooks Davis, Mr. David Lindels, Mr. Carl Lockhart, and our eternal friend B.S., and Randy Dalzell, Ms. Tina Raudio, the enigmatic Ryan, a gentleman named Crux, and Gabe and Evan Weens, David D., and Dan Vale, Mr. Alex, WTL, Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, and John Bleasy. Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's Gang of One, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Andreas from Knoxville, Cadby, Joe Campbell, Alexander Zani is Great, Weena Brett, Eric Deutsch, Etienne, and a gentleman named Peter Fan. Gareth Eason, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, Mr. Frank, Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Ouarzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, and Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shire, Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, and Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Read, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for Titanium Physicists this time, everyone. Remember that if you like listening to scientists talk about science in their own words, there are other lovely and new shows on the Bracula Media Network. So go drop by the BMN and check them out. The intro song to our show is by Ted Leo and the Pharmacist, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hopped down Magnolia Boulevard. No way he'll survive.
All right.
I forgot my RAR sound. I think it was RAR.
I don't know. I can't remember. I'm sure it'll be fine.
Yeah.
Maybe it was a bit more. Maybe it was a bit more Mutant Enemy, RAR.
Yeah. I think I well, I was influenced by children's television.
Sorry, am I allowed to say Jesus?
No, not on this podcast.
sorry. Jeez Louise.
Correct.
That's wow, that's wild. So like
Holy moly, yeah.
Yeah.
Not holy. What's the word? Non-denominational.
You can't say holy moly.
No, holy non-denominational.
Roly moly.
I think is the proper.
Jinkies.
Holy moly. Sorry, I said holy again.
Jinkies.
Oh, jeez.
If you
Gotta edit that out.
now these things don't.
We need a list of approved. That's approved. Isn't it? It's an ejaculation, but that now sounds even worse.
All right, here's ejaculations that you can't use. You can't use ejaculations talking about God or Jesus or any reference to the existence of any organized religion whatsoever.
Do you,
Well, I mean, sorry, go
beans
ahead.
and rice.
I was
Okay, I'm being silly. I don't care. Get back to work, Jocelyn.
Right, no ejaculations of the cloth.
We have lots of material, and we've covered everything on my list of things that are worth covering. Have you got any questions, Charlie, before we end the show?
Oh, I've got 20 million questions, but I'm afraid that they would all.
You can ask a few of them.
No, absolutely.
No. I mean, I like they're not even fully questions yet. Like I feel like now I have this, childlike awe that might that might crystallize into a question, in the coming days and weeks. But it's just a neat. I don't know. My daughter is she's about to turn 4 in January, and she's just learning about planets, and so she's been excitedly explaining to us about Venus and Jupiter, and this is this is the order of magnitude of thing you have to learn about to go back to having that same kind of feeling of just kind of total wonder and partial understanding. But it's really neat.
Yeah,
that's what our show is all about.
Yeah, that's the fun of science, is you can just be like a 4-year-old forever going, what?
Yeah. That's actually why we do what we do.
Ben, if your podcast is about teaching me the glory of God's creation, then you have done it. Thank you guys so much.
You gone and ejaculated again.